Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we've been working through the brand new June 2026 Chemistry Regents. This is the 7th video in the series where we tackle the iodine clock cluster. If you're looking for a different cluster, you can check out the playlist in the description where you'll find step-by-step walkthroughs for the rest of the exam. Let's get started. The first step is going to be to thoroughly read the cluster for understanding. So in clock reactions, the completion of the reaction can be timed due to an observable change, usually a color change. A student performs one type of clock reaction to determine the effect of temperature on reaction time using mixture A and mixture B, which contains starch. The reaction time is measured from the initial combination of mixtures A and B to the point of an instantaneous dark blue color change. Figure 1 shows the materials and this color change. Table 1 lists student data and calculated reaction rates at 4 temperatures. During this laboratory activity, appropriate safety equipment was used and safety precautions were followed. All right, so it gives us experiment number, the temperature at which a reaction is formed, the reaction time, and then the reaction rate. And this right here, I'm assuming for most of you, is probably a new unit. Side thing, teachers, if you're watching this, I highly recommend doing this in class. I have a sulfur clock reaction lab that I'm happy to share if you leave a comment. But getting back to the chemistry of this, if we think of reaction temperature and reaction time, you might struggle a little bit with the relationship because what I think of is rate and temperature. I know if I increase the temperature of a reaction, I'm also going to increase the rate of a reaction, right? There's a few different things we can do to increase the rate of a reaction, right? Like we can increase the concentration of reactants. We can increase the surface area. We can increase the temperature. We can increase the pressure if it's a gas. We could add a catalyst. We also know that generally ionic compounds have a higher rate of reaction than covalent compounds. I digress. Let's move along. So for question 28, it says a student completes experiments 1 through 3 and claims that as temperature increases, the reaction time increases. Place a check mark in place a check mark in either the support or refute box below to indicate if the given information supports or refutes the student's claims. Provide numerical evidence to support or refute the claim. Okay, so we got to go look at the data, and we know if we don't put numbers down, we're going to get the question wrong. So student says, as temperature increases, reaction time increases. So let's look at the trend. If we look at this temperature, 283 to 313, the time at 283 is 459 seconds. The time at 313 is 52 seconds. So that is not correct. As the temperature is increasing, the reaction time is decreasing. Right? So I'm going to say time decreases. Okay, so think about it. Like if you have a lower time, that does mean that you have a higher rate. So kind of picturing those relationships can be a little bit challenging, especially when you're throwing these units that you don't really know what they are. But anyways, I think we have enough information to refute this claim. Evidence that we should provide is something with numbers. So I cited those 2 experiments, 1 and 4. So let's write something up. So I said experiment 1 had a time of 459.0 seconds at 283 Kelvin. Experiment 2 had a lower time at 313 Kelvin. All right, question 29 says the student performed a 5th experiment using the conditions of experiment 2 in the table. In this experiment, copper plus 2 aqueous was added to determine if the ion acts as a catalyst. Which reaction rate would indicate that the copper plus 2 acts as a catalyst? Well, remember, a catalyst is going to increase the rate of reaction. All right, if we are simulating experiment 2, what I want to know is what was the rate of experiment 2? This way I can compare it with the answer choices. So right here, it is 3.95 times 10 to the negative 6 molar per second. All right, so if this copper plus 2 truly acts as a catalyst, the rate should be higher than the rate that we just wrote here. So let's evaluate the answer choices. 3.15 times 10 to the 6, that's lower. 3.15 times 10 to the negative 5th, that's going to be higher, right? Because if you think about this, this will have 1, 2, 3, 4 zeros in front of it, whereas this one to the negative 6 will have 5 zeros in front of it. Right, so this answer choice shows an increased rate. These ones are also wrong because they're both lower. All right, a different clock reaction uses 0.100 molar potassium iodate, KiO3, with a molar mass of 214 as mixture C, starch, and 0.250 molar sodium bisulfite, are used for mixture D. The alarm in this clock reaction is the color change that occurs when the formation of molecular iodine reacts with starch. Molecular iodine is formed after a sequence of reactions involving mixtures C and D. Equation 1 represents the first step in the sequence. Equation 2 represents the simplified conversion of iodine ions to iodine molecules. And question 30 says, which phrase identifies an acid and its property in equation 1? Okay, so if we look at the answer choices, we're talking about hydrogen ion donors and hydrogen ion acceptors. So it doesn't hurt to know if you are a H plus donor, that's going to make you an acid. And if you're an H plus acceptor, that's going to make you a base. Okay, so let's go ahead and assess the answer choices. So is this an acid? Well, we have HSO3 minus, and then that is going to become SO4 minus 2 and 3 H pluses in solution. I am thinking that this is donating hydrogen ions, even though we don't see where they're going. It's really the only thing here that actually has hydrogen ions to release. So it's got to be choice 1. Right? It's certainly not accepting hydrogen ions because it's starting as HSO3 and then it's ending as SO4 minus 2. So what it's accepting is an extra oxygen. IO3 minus cannot be a hydrogen ion donor because it doesn't have hydrogen ions. And there's really no evidence to show that IO3 minus is accepting hydrogen ions. Thus, choice 1 is the best answer choice. Right, a student makes a claim that the conversion of iodine ions to iodine molecules is oxidation based on evidence from equation 2. Which statement demonstrates the validity of the claim? So you're probably thinking either Leo the lion goes grr, lose electrons oxidation, gain electrons reduction, or oil rig, which I personally teach my students because America. Oxidation is loss, reduction is gain. So anyways, oxidation, we are looking for the loss of electrons. Okay, so we are going from -1 to 0 oxidation state. We know that this is a state of 0 because it's a free element, and here it tells us the oxidation state. What we are doing is we are getting more positive. If we are becoming more positive, that means that we are losing electrons, which are negative. All right, so right off the bat, we can eliminate 3 and 4 because they incorrectly state the change in oxidation state. Choice number 1, the oxidation changes to -1 to 0 because I2 loses electrons. I2 is not what's losing electrons. I2 is what's forming when the two I minuses lose electrons. All right, so we want to pick the choice that says I minus is losing electrons. Right, and then then question 32. The teacher prepares 250 milliliters of mixture C. How many grams of solute are required to make the solution used in this clock reaction? Looking at our reference table, this is going to be an N equals MV type question. All right, we know that volume must be in liters. So our volume, if we convert that to liters by dividing by 1,000, is going to be 0.250 liters. Going back to the passage, it says that the clock is using 0.100 molar potassium iodate, and it's defining that as mixture C very explicitly here. So our M for molarity is going to be 0.100 molar. And then we're going to be left solving for N, which is not the gram value, it is the mole value. But once we have the moles, we can then convert it to grams. All right, so solving this equation, we can get that N is equal to 0.0250 moles. And that would be moles of potassium iodate, KiO3. Right, which it gave us the molar mass of, right? We know that 214.00 grams of KiO3 is equal to 1 mole of KiO3. So then we just have to convert that mole value that we just solved for. Right, so that comes with some dimensional analysis. So I will start by writing the moles on top. I want to get rid of it, so I'm going to put moles of KiO3 on the bottom. I put grams of KiO3 on top. Plugging in the numbers, this is what I get. And when you multiply 0.025 by 214, you end up with answer choice 3, which is 5.35 grams of KiO3. So that's it for this cluster. If you found this helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can click the next video. I'll link the playlist in the description, and hopefully it should pop up. Happy studying.